Okay, so I'm going to go over the exam review 3. So this is the third review that he posted. This one looks fairly long, so I expect this video will be fairly long. Um, yeah, so let's get started. So, number 1, find the domain and range of each of the following functions. So part A is the function f of xy is ln of square root 1 plus x squared plus y squared. Okay, and incidentally, this is the same as 1/2 ln of 1 plus x squared plus y squared. Okay, so now the question I want to ask is, are there any values where this is undefined? Okay, well, when is natural log undefined? Natural log is undefined when whatever's inside is less than or equal to 0. Okay, and the places where it's undefined are going to be the values that are not in my domain. Okay, so is this possible for this to be less than or equal to 0? No, it's not, right? X squared is positive, or it's bigger than 0, bigger than or equal to 0. Y squared is bigger than or equal to 0, and we have this 1 here. So this thing on the inside, so I'll put a question mark here, is that bigger than or equal to 0, or less than or equal to 0, anywhere? The answer is no. So this means that all pairs of x and y are in my domain. Okay, so the domain is going to be the set of all possible values x, y, such that um, x is any real number and y is any real number. There's a number of ways of writing this. We could just say that the domain is equal to r2, r squared, right? So that means all of the possible pairs of two real numbers. But something like this will be fine. Um, Another way of writing it, you could have x, y, such that minus infinity less than x less than infinity, and minus infinity less than y less than infinity. That would also be fine. Um, okay, now what is the range for this function? So the range is the set of possible outputs of this function. Okay, and so we know that the minimum value of this thing on the inside, or actually, so what does natural log look like? Natural log as a function, well, of just x, right, of whatever this is right here, looks like this, right? And technically, it keeps going up and up and up off to infinity, okay? And it keeps going down and down, down, down to negative infinity. So here, what is the minimum value that we're inputting? Okay, well, actually, let me finish that last thought. So here, the main point that I want to take away is that this function, it's always increasing, and it goes off to positive infinity. Okay, so what's the minimum value that we're inputting here? Well, like I just said, since this is always bigger than or equal to 1, the minimum value that we're inputting is 1, and that's going to be right here. So the possible outputs of this function are going to start at 0, right? And that's going to be all of the values up along here, because we know that this function goes off to infinity. So I'm looking at all of the values on this side, right? So it's going to be all of these values. That's going to be my range. So the range, notice it's not the real numbers, the range is going to be the set of all numbers, let's call it z, all real numbers, such that z is bigger than or equal to 0. Right, if x squared and y squared are both 0, then ln of 1 is 0. So we get the equals to 0. So the range is the set of all the possible outputs, and the domain is the set of all valid inputs. Okay, so B. F of x, y, z is x squared plus y squared plus z squared minus 1. Okay, so when is this valid? What are the valid inputs? Well, I know that the denominator can't be 0 because I would be dividing by 0. And I know that whatever's on the inside of the square root can't be, well, so that can't be 0 either, but that can't be negative. So that means that the points where this, what I'm about to write, is true, the points where this is less than or equal to 0 are all of the points that are not in the domain. Okay, so these are all the points x squared plus y squared plus z squared. I'll add 1 to both sides. So all of the points where this is true are the points that are not in the domain of this function, right? Because if I have something like this, then it means that this is going to be negative and I can't have that. Okay, so the domain is going to be the set of all pairs x, y, z such that x squared plus y squared plus z squared has to be bigger than 1. Okay, and what about the possible range? Well, we know that, let's see, so we know that we're always going to get a positive number out of here. Okay, um, and we're never actually going to be able to plug a number in and get um, 0, right? Because we can do the limit as this goes off to infinity, right? X, Y, Z get really, really big, and we'll get close to 0, but we're never going to actually get 0. So the range is going to be the set of all, I'll call it R. Okay, so we know that I can never actually get 0. It's gonna get close, but not quite. And then what's the maximum value? Um, so if x, y, z go to 0, or if these are really, really close to 1, right? So it's really, really close to the border here. This is going to get close to 0, right? X squared plus y squared plus z squared minus 1. That's going to be really close to 0. So I will be dividing by a very small number, which gives me a very big number. Basically, that's going to go off to infinity, like this. So in a 2D sense, right, I have my domain is out here, right, and that has a radius of 1. And if I get close, the limit as I get close to the edge, it's going to go off to infinity as I get closer and closer to the edge, right, because I'm getting closer and closer to dividing by 0. And as we go this way, so this goes off to infinity going this way. If I go off this way, 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 way out, it's going to be going to 0. So the possible outputs from this function are going to be all of the possible numbers between 0 and infinity. Okay, next question. Okay, it says identify the level curves or surfaces of each of the following functions. So a, f of x, y is e to the minus 4x squared minus y squared. So what are the level surfaces? So let's set this equal to some constant, e to the minus 4x squared minus y squared. I'll take the natural log of both sides. So this is minus 4x squared minus y squared. And then let me just move everything around. So I'm going to have 4x squared plus y squared equals minus ln of k. Or actually, if I rewrite this, I have x squared plus y squared over 4 equals 1 over 4 ln of 1 over k. All right, so here, this is some constant, okay? It depends on what k is. If k is close to 0, then this constant is going to be very, very large. If k is very, very large, this thing is going to be quite small. Or it's going to be very naked. K has to be bigger. So here, k has to be bigger than 0. So if k goes to 0, that goes to infinity. Okay, yeah. And if k goes to infinity, that goes to 0. Yeah. Okay. So what are these shapes? These are all ellipses. So it's going to have 2 in the y direction and 1. Oh, no, I'm sorry. That's why I was getting confused. Okay. No, because I don't want to divide through by 4. I want to divide through by this other number, ln of k. So that's 4. 1 over ln 1 over k. All right, so these level surfaces, what do they look like? Like I said, they're ellipses. Um, so they're going to be kind of long in the x direction, but not as long in the y direction. Right, so I'm going to have an ellipse. And this distance here, that's going to be ln of 1 over k. And this distance here, that's going to be 4 over ln of 1 over k. Okay, so the set of all these ellipses are the set of all the different level curves. Okay, next one, B. We have f of x, y, z, 2x plus 3y plus 6z. Right, so this is a function, it spits out a scalar. And if I look at these, I'm going to write this as 2, 3, 6 dot x, y, z. Okay, so we know that this actually describes a plane, right? So if we set this equal to some constant, it's going to describe a plane. And they're all going to have the same normal, right? This is the normal vector. But if we change this, it changes which plane we have, right? So we might have a plane like this, but then we might have another plane that's still facing the same direction, but slightly higher, or even higher still, right? These are all parallel, right? So it's a family of parallel planes. They all have the same normal. They all have the same normal, but just which plane you have depends on what the value of k is. Um, So your answer is going to look like describing what I just said. Basically, here it's describing a family of ellipses, right? So you want to be kind of specific about this, right? So these are a whole bunch of ellipses. And here we have a family of planes. Okay. Um, Next question. Okay. Um, Technically, this is part C, but it says an open container, no top, is to have a volume of 12 cubic feet. Um, so let me just draw this real quick. We have a container here, here, with no top. So I can draw it like this. Okay, but it's not going to have a top. So the height is going to be h. This will be the length and the width. So we know right away that the volume is length times width times height. Okay, now let's finish reading the question. The material for the sides is $3 per square foot. So the area of the sides, um, A sides, the area of the sides, that's going to be 2. So we have two sides where it's the length times the height, and we have two sides where it's the width times the height. And we know that this costs, the question says $3 per square foot. So the cost for the side is going to be $3 per square foot. How many square feet do we have? It's going to be 2 times LH plus 2 times WH. Okay, same thing for the bottom. So the area of the bottom is going to be just the width times length. So the cost for the bottom is going to be, let's see, so the question says the cost for the base is $5 per square foot. $5, so that's going to be 5 times W times L. Okay, so the total cost total is going to be, so it's going to be yeah, okay, so this is going to be 6 LH plus 6 WH plus 5 WL. But from over here, what do we know? We know that H is, it says, yeah, H is equal to V over LW, which is 12 over LW. So I plug that in, and I get that this is equal to 6 times 12 is 72 over W plus 72 over L plus 5WL. And that's my answer. And the question phrases this in terms of this is X and this is Y, but you get the same answer. So it doesn't, or it says the length is X and the width is Y, but it doesn't make a difference. Okay. Question 2. Let f of xy equal 2x squared y over x to the 4 plus y squared. And we're interested in the limit as xy goes to the point 0, 0 of this function. Okay, so real quick, I see I have x squared and a y on top. So this is kind of like something cubed. I can think of it kind of like that. And on the bottom, the highest order power is to the fourth. So this means that I'm going to have the bottom going to 0 faster than the top, meaning that this is probably going to blow up or go to infinity and not converge to a limit. So that's just a guess. Okay, that is totally just a guess. So let's actually compute some of these limits. Okay, so here it says, let's compute this limit. So part A, along the x-axis. So what does that mean? It means I take the limit as xy goes to 0, but I'm holding y as 0. Okay, so I want the value here, but I'm going to take the limit as I get close in this direction, right? So this is y equals 0, and x is going to 0. So that's going to be the limit. So that's already 0, so we have the limit as x goes to 0. And I plug, let's see, so that's going to be 2x squared. Y is 0, so that's 0 over x to the 4 plus 0 squared. So that's 0. This whole thing is just 0. Cool. So this gives me a first guess that the limit of this function, if it exists, I don't know that it does, actually I think it doesn't, but if it was to exist, it should be 0, because all of the limits should be the same if it exists. So since I think that this doesn't have a limit, then I'm looking for a way to get something other than 0. So B, we're looking for the same limit, except let's do this now along the y-axis. So we do the same thing, except now we do 0, x is 0, y goes to 0, 0. So now we're going along this direction. So we do the same thing. This is limit, but this time y is going to 0. And we have 2 times 0 squared, y over 0 plus y squared. And same thing, we get 0. Okay, that's fine. You know, because it's okay to have, you know, even if the limit doesn't exist, it doesn't mean all of these limits are going to be different. It just means at least one of them is different. Okay, C, it says do the limit along the line y equals mx. So now we're doing this along like any slope like this, right? So I'll treat m as a variable. That should be a line. And C, we'll probably see that it doesn't matter. So this is the limit as x and mx go to 0, f of x mx. So that's going to be, I have 2x squared m on top over x to the 4 plus m squared x squared. Okay, and now we still want the limit. Oops. So we're looking at this thing and we still want the limit. But now we just need to let x go to 0. Okay, so if I plug in 0, I get 0 over 0. So I'll use L'Hopital's rule. So this is going to be the limit x goes to 0 of, I do the derivative of the top, which is going to be 4xm, and the derivative of the bottom, which is 4x cubed plus 2m squared x. I plug in 0, and again I get 0 over 0. So I do L'Hopital's rule again. So that's L'Hopital's rule. So I do the derivative of the top, and I get 4m. I do the derivative of the bottom, and I get 12x squared plus 2m squared. Okay, so I plug in 0, and I get 4m over that's 0. I get 2m, which is just 2. No, that's not right. This should be squared. Okay, so I cancel that out, and I get 2 over m. Is that right? So if the slope is, that should be 0. Let's see, let me just double check that real quick. So I plug this in to here, right? So I have x squared y. Oh, I see. This should have been x cubed, because I have x squared times mx, so that's x cubed. So this would be 6x squared. That stays the same. But it means we're going to have to do this derivative one more time. So I do the derivative, I get 12x m, and I do the derivative one more time, and I get 12m over 24x. Right? Yeah. So that cancels, and I get a 2. So this is going to be m over 2x. When we do the limit as this goes to 0, the limit goes to infinity. But why? I still think I'm doing something wrong. 1 second. So we plug mx, we plug this mx, m squared, x squared. We do the derivative. Okay. Oh, I see, I see. Okay, so yeah, so this is going to be um, either we want to say infinity, or does the limit does not exist. Okay, so notice real quick here, how does this line up with the zeros that we got before, right? Because if the slope is just a line, we know that these are just lines also. So this line right here, the x-axis, that's the case where the slope is 0, right? So that means that m is going to be 0. So this lines up with what we had before. In this case, the vertical line, that's the case where m is infinite, and x is also going to 0, so we have kind of an indeterminate form, which when we actually work it out, we would get 0, like we did. Okay, so now, this one, I don't think we ever did one like it. It tells us to do the limit along the parabola y equals lambda x squared. So this corresponds to doing the limit as I go along a parabola. Now which one depends on which lambda I pick, but I'm still always going to the same place. It just depends on a parabola. Okay, so I do limit x lambda x squared goes to 0, 0, f of x lambda lambda x squared. So I plug this in and I get limit x goes to 0 of, so I have 2x squared times y, and y is going to be lambda x squared. Here I have x to the fourth plus y squared, so that's going to be lambda squared x to the 4. Limit as x goes to 0. So here I have 2 lambda x to the 4 over 1 plus lambda squared x to the 4. Those cancel out, and I get just 2 lambda over 1 plus lambda squared. So the limit here, it depends on which parabola I take. Quite a lot, right? If I take a different parabola, I choose a different lambda, and I'm going to get a different limit. So the last question, can we say that in general the limit as x, y goes to 0, 0 of this function, does this limit exist in general? The answer is no, because different paths give different limits. Okay, and when I say path, I mean the direction in which we approach the origin. Right, so if we go in along this way, we get something different than if we pick any one of those. Okay, next question. We're given the function f of xy is y squared e to the xy plus x over y. And it says calculate fxx and fyx. Okay, let's do this one. So first, in each of these, I first need to compute the x derivative, the partial with respect to x. So df dx.
Mic off. Mic on.
So this is going to be y squared, no, it's going to be y cubed e to the x y, right? Because I have to use the chain rule when I do the derivative, so I bring the y down, and I have y cubed now. And here, derivative with respect to x, that's just going to be 1 over y. Okay, so now I want the x derivative of this, right? So the partial with respect to x of this thing, right? And this is what we call the d squared f dx squared. So it's the derivative of this thing with respect to x. So again, I'm going to have to use the chain rule. I bring the y down, and I get y to the fourth e to the xy, and then that has no x's in it. It goes away. Okay, so now this one, I need the y derivative of this thing, right? So this is asking for dy of df dx, which is d squared f dy dx. Okay, so now I'm doing the derivative of this with respect to y. So here I have to use the product rule. So that's going to be y to the fourth e to the, oh sorry, no, that's not right. It's going to be y cubed x e to the xy, right? The derivative of this with respect to y, I have to bring down the x. plus 3y squared e to the xy, and then minus 1 over y squared. And those are my two derivatives. Okay, that was part A. Part B, it's going to be ln of square root x squared plus y squared. And it says show x dz dx plus y dz dy is 1. Okay, so let's calculate these partials. Um, just because I don't like working with square roots, I'm going to write this as 1/2 ln x squared plus y squared. So dz dx, that's going to be 1/2 derivative of natural log, that's 1 over. And what we have here, we have x squared plus y squared. It's not just x, so I need to use the chain rule. That's going to be times 2x, the 2's cancel, and I get x over x squared plus y squared. Okay, now I do the same thing for dz dy, and it's going to be basically the same thing. I have 1/2 1 over x squared plus y squared, chain rule, 2y, the 2's cancel, and I get 2 over x squared plus y squared. Okay, so let's plug this in. So I have um, see, times x over x squared plus y squared plus y times y over x squared plus y squared. And I get x squared plus y squared over, and I add the terms, and I get x squared plus y squared over x squared plus y squared, which is 1. And we've showed it, so that's what the question told us to do. So we're done. C. It tells us that u equals x squared minus 2y squared plus z cubed, and it tells us that x equals sine of t, y equals e to the 2t, and z equals 3t. I'm going to write this real quick as r of t. That's going to be sine, well, that's x of t, y of t, z of t. So this is going to be sine t e to the 2t, 3t. So we want the derivative of this with respect to t.
Mic off. Mic on.
Okay, so u is technically a function of t because x is a function of t, y is a function of t, and z is a function of t. Okay, so I could technically plug each of these in and then do the derivative with respect to t, okay? But that'd be a lot of extra work because I can use the chain rule, and this becomes gradient of f at r of t dot r prime of t. Okay, so let's compute the gradient. So not gradient of f, this is the gradient of u. So grad u, that's going to be 2x, let me do this as a row vector. 2x minus 4y 3z squared. Okay, so this particular problem doesn't give us values for x, y, z or values for t, so we'll just leave it in general terms. Um, but I do want it in terms of t. So let me go ahead and plug x, y, and z into here. So this is going to be, so gradient u at r of t. So this is 2 sine t minus 4e to the 2t, 3 times 3 squared, which is 27 t squared. So then finally, grad u dot, oh, not quite. So now we want r prime. What is r prime? R prime of t, that's going to be cosine of t, 2 e to the 2t, and 3. So our final answer, gradient of u dot r prime, that's going to be, so it's 2 times sine times cosine. That's, I'm going to simplify right away. That's, no, I'll do an extra step. So I have 2 sine t cosine t plus, here I have minus 4, so that's a minus already, e to the 2t times 2e to the 2t plus 3 times 27, that's 81 t squared. So I simplify, this is sine of 2t minus 8 e to the 4t, right, because they're multiplied, so I add them together, plus 81 t squared. And that's my answer. Okay, so one more with the chain rule. Here we have, see, this is part D. So we have z equals e to the 2x ln y. And it gives us that x equals u squared minus v, and y equals v squared minus 2u. And it tells us to find dz du and dz dv. Okay, so this one isn't as easy, right, because I can't just do this dot r prime thing. Okay, but what I can do is I can write it like this. dz du, that's equal to, um, so I can't take the derivative of z with respect to u because there's no u in there right now, but I could write this as derivative with respect to x, dz dx times dx du, right, as if these cancel out. But I have to make sure to not do it for just x, I need to also do it for y. And this is exactly what we're going to compute. Okay, so this dz dx, that's going to be 2e to the 2x ln y times dx du. So the derivative of this with respect to u, dx du is going to be 2u, yeah, so times 2u, plus dz dy, that's going to be e to the 2x over y times dy du. That's going to be minus 2. Okay, so I simplify and I have 2e to the 2x times 2 ln of y minus 1 over y. Okay, and now I do the same thing, dz dv. So I can just write this as the derivative with respect to whatever variables there are. I'll fill that in later. And I repeat that however many times for however many variables I have. Sorry, this is not u anymore, right? I want the derivative with respect to v, right? So that's going to match here and here, right? So that should actually be a v. Okay, so our two variables that we have, that's going to be x, y, y, and I start computing. So dz dx, we already know what that is. That's going to be 2e to the 2x ln of y times dx dv. So if we look up here, x is u squared minus v. Dx dv is going to be negative 1. So I'll just put that negative right there. Plus dz dy, that's going to be the same also. So that's e to the 2x over y times dy dv. That's minus 2. dy dv is going to be 2v. Where did my u go? It looks like I lost this u somewhere, so that should be ln. I'll just put it up front, so that's going to be 2u. Okay, times, so I said dy dv is going to be 2v, so I multiply by 2v. And I can simplify this as 2e to the 2x minus ln minus 2 ln y plus, nope, I factored out that too, v over y. Okay, so we're almost done. Notice real quick though, here I have a u and a y and an x. So I kind of have like these variables mixed up. I want to separate it out so that's only in terms of of either u and v or in terms of x and y. So the easiest way to do that is just to replace x and y with this right here, right? So here I'm going to have 2 e to the 2x, which is 2u squared minus 2v, times 2u ln of y, which is v squared minus 2u, minus 1 over v squared minus 2u. Right, so now it's all in terms of, one set of variables. And same thing here. So that's the same, e to the 2u squared minus 2u times minus ln of y, which is v squared minus 2u, plus v over v squared minus 2u. And those are my two answers. Okay, moving on to the next question. Man, this is I'm probably going to break this into 2 videos because this is quite long. So I'll probably cut it off at about an hour. Okay, so the question number 4 gives us f of xy equals x tan inverse y over x, and that f of x, y, z equals x squared plus 3yz plus 4xy. Okay, so 1, or I, is find the gradient of f. Okay, so that's pretty simple. The gradient of capital F is what it's asked for. So that's going to be 2x plus 4y. And then with respect to y, that's going to be 3z plus 4x. And then with respect to z, so that's going to be 3y. Done. Determine the direction in which little f is increasing most rapidly at the point 2, 2. It's decreasing most rapidly. Okay, so this is slightly different than the other reviews where it was asking about increasing, but it's not any different. So the direction that I want is the direction of the gradient at the point 2, 2. Almost. So this is the direction of steepest increase. If I want the direction of steepest decrease, I take the negative of that, right? So if I'm if I have some sort of surface and I'm looking straight down at the surface, right? If that way is the steepest increase, it means that that direction in the opposite direction is the steepest decrease. At that point. Okay, so let's find the gradient of little f. So that's going to be, let's say I need to use the product rule for the x derivative. So we'll have tan inverse y over x plus x times the derivative with respect to x of, you know what, let me write this out separately so that it's easier to see. df dx, that's going to be tan inverse y over x plus x times 1 over 1 plus something squared. I have y over x, so I need to multiply by negative y over x squared. Okay, I put this over a common denominator, and what I get is tan inverse y over x plus, nope, minus xy over x squared plus y squared. Okay, and then I want df dy. So this is a lot simpler. This is going to be x times 1 over 1 plus something squared. I have y over x, so that's just times 1 over x. Right, I have to do the product rule. That cancels, so I end up with x squared over x squared plus y squared. So that's going to give me the gradient. The gradient of f at 2, 2. Now remember, I need to take the negative of this when I'm done. So I'm just going to plug in 2, 2 real quick. So that's going to be tan inverse of 1 minus 4 over 2 squared plus 2 squared. That's 4 plus 4, that's 8. And then here I have 2 squared, that's 4 over 8. So negative gradient f at 2, 2. So the inverse tangent of what? That's pi over 4? Yeah, So this is going to give us 1/2 minus pi over 4 and minus 1/2. Okay, so this is going to be the direction. I could normalize this to get a unit vector to actually have a unit direction. Um, but just like with the ones with the steepest increase, the rate at which it's decreasing is actually just going to be the norm or the norm of this vector. And the reasoning is exactly the same as the other the other videos. So I take the norm of this and I get 1/2 minus pi over 4 squared plus 1/2 squared. I'm not going to bother simplifying that. I think that's fine. That's the rate at which it's decreasing, and this is a vector in the direction that it is decreasing the steepest, the fastest. I still need the gradient. Okay, 3. It says find the directional derivative. Oh, okay, so I need to scroll up even more. Okay, find the directional derivative of f, capital F, at the point 1, 1, minus 5 in the direction of a, which is 2, 3 minus root 3. Okay, so here, the directional derivative, we know that's going to be gradient of f at my point dot a hat. The hat means that I need to normalize it because it probably doesn't have a norm of 1. So norm of a is going to be square root of 4 plus 9 plus 3. That's 16, so that's going to be 4. So a hat is going to be 1/2 3 over 4 minus root 3 over 4. And the gradient of f, let's do that here, at 1, 1 minus 5. Well, we know what the gradient of f is from right up here. This is going to be, let's see, 2x plus 4y. 2x, that's 2, plus 4y, that's 6. 3z, that's minus 15, plus 4, minus 11. And then 3y is going to be 3. So now I do the dot product. Gradient of f dot a hat, that's 6 minus 11, 3 dot 1/2, 3/4 minus root 3 over 4, which gives me, I'm going to leave this as 2 over 4 for fractions. So that gives me 12 over 4 minus 33 over 4 minus 3 root 3 over 4. 22 minus 33, that's minus 21 over 4, and that's my answer. Yeah. Okay, so now it says find an equation for the tangent plane at the point, no, sorry. Um, find an equation for the tangent plane to the level surface so we're describing a surface. It's all of the points where this equals 3, right? So that describes a surface. Find the tangent plane to that surface at the point 3, minus 1, minus 2. Okay, so we know that the vector that is orthogonal to this level surface is going to be the gradient, right? Because gradients are orthogonal to level sets. So the normal vector for the tangent plane that we're looking for is going to be this, which is, I'm just going to copy this over here. That is not it. Oh, it's not letting me copy it. Why not? There you go. Okay. So the gradient at, so that's 2x plus 4y. It's going to be 6 minus 4. And then I have 3z, that's minus 6, plus 4x, 12. And then 3y, that's minus 3. Let me make sure I did this right up here. So I had 3z, 3z is minus 14 plus 4x. Okay, so it doesn't matter. Okay, so that's my normal vector, and then I have my point on the plane. So I can write this down very quickly. This is just going to be 2x minus 3 plus 6 y minus minus 1 plus, it's going to be minus 3 times z minus minus 2, it's plus 2, equals 0. That's my equation for the tangent plane. Okay. Next it says find an equation for the tangent plane and the scalar parametric equations for the normal line to the surface. So it talks about the surface z equals f of xy. So we want the tangent plane and the normal line to this surface, the xyz surface, at the point 2 minus 2 minus pi over 2. Okay, so I need to move all of my variables over to the one side. So I'm going to have, let's do f of xy, let's see, put this as part D, minus z equals 0. So this is what I want to take the gradient of, okay? I already know that so this is going to be, let's call this big thing, let's call this g. So this big thing is g of x, y, z. And the gradient of g is going to be equal to the gradient of f plus gradient of minus z. I know what the gradient of f is. It's this. Well, I didn't write down explicitly. Okay, so it's tan inverse y over x plus or minus minus xy and then x squared. Okay, and then gradient of minus z, so that's going to be 0, and then gradient of minus z, right? That's obviously just 0, 0, minus 1. Okay, so that tells me that gradient of g is this, and I'm going to plug in these numbers. So I have 2 minus 2, so that's tan inverse of minus 1. Minus, that's going to be actually plus 4 over 2 squared plus 2 squared, that's 8. And then I have x squared, that's going to be it's going to be 4 over 8, and then minus 1. It's going to be my gradient of g. Okay, so we have 1/2, and then we have plus 3 pi over 4. See, is that how we want to do it, or do we want to do it the other way? Let's go minus pi over 4, because that's the range. 1 over 2 and minus 1. Okay, so that's my gradient. So that's gonna for the tangent. That's for the tangent plane. That's gonna be the normal line, and then for the normal line, sorry, this is gonna be the normal vector for the tangent plane. For the normal line, this is gonna be my direction vector. Okay, so I can write down the tangent plane right away. I have 1/2 minus pi over 4 times x minus 2 plus minus plus 1/2 y minus minus 2 minus 1 times z minus minus pi over 2 equals 0. That's my tangent plane. If I want the normal line, so that's my tangent plane. If I want the normal line, let's see, it says write the scalar parametric equations. I'm going to have gradient of f times t plus a point on this curve, which is 2 minus pi over 2. Okay, so here I have x of t is going to be 1/2 minus pi over 4 t plus 2. Y of t is going to be 1/2 t minus 2. Z of t is minus t minus pi over 2. Okay, so I'm going to go ahead and cut this stream off because it is quite late and this is barely halfway. So I'll be posting the second half of this tomorrow. Well, I guess later today, technically.